Okay, so I did not get a chance to finish these, so what I would like to do is I would like to go back and talk about some of these questions. Look, I may go back to the very beginning so that you can kind of get a better idea of what type of things I'm envisioning, and then we will go from there. So I'm hoping that at least the illusions and the building of the shapes, if nothing else, gave you an idea of what the figures will look like. One of the things that students really struggle with on this topic is just trying to imagine what type of shape is happening, and it's really it produces some neat shapes. We're able to now start calculating volumes and areas and things like that. Just for example, if you take a look at my pencil holder on the front, it's a shape that we could create using cross sections and an area. So it becomes kind of an interesting little setup. With that said, it's not necessarily always going to be the simplest thing to do, but if we think about the unit conversion concept, if we think about if f is in centimeters squared, then if we do f prime, that would take us to centimeters, and if we do an integral, that should take us to centimeters cubed. So there's a little bit of a relationship with the units that needs to get used to. And one of the things to remember as we go through this is the idea that if we have an area of a cross section, okay, some a of x, this is actually often rewritten as v is equal to the integral from a to b of just a of x dx, or the integral from a to b of a of y dy. So we can either do a function in terms of x or in terms of y. But the idea is we can find the area of the cross section very easy, and that's a little sliver here. And if I start taking this cross-sectional area here, and if I start realizing that I could have a whole series of rectangles that I'm going to build off of, that if I were to add these widths of these rectangles across, I would eventually wind up with a volume. And remember that this dx, it's multiplying the area, so it's an x times an x area function, and this dx is originally very small, but remember that we're adding together all of those dx's from a to b, giving me a third dimension inside of our problem. So there's some really cool dimensional analysis that goes into this. So what I was talking about earlier with the squares, for those of you that were unsure of the square question, was if we think about how the area of a square works. Area of a square is simply the side length squared. So for instance, if I were to draw this, and if I were to look at this as a three-dimensional shape, we might have, I don't like the way I did the perspective. Maybe that'll be a better perspective. There you go. Sure. Imagine that this is down along the bottom and that this is popping up at us. So what happens is that this would be a square that would be whatever this f of whatever this is, and this side would have the same length. Well, it should also not be a surprise then that if I select a different location, what will happen is that that particular square should be a little bit larger. Why? Because this side is a little bit smaller. But as I move further up the ladder here, and I get up to, say, this value, the square should be getting a little bit smaller. So we can see that this distance gets a little bit larger, gets larger, starts getting smaller until eventually, we're way up here. We've got this square that's going on up there. And you can see that there should be a three-dimensional shape that will be created from this. Again, this is kind of hard to see because we don't really have a perspective. Oh God, I can't believe I'm going to attempt this. If I attempted to turn this, let's call this the y-axis. Let's call this, actually don't want to put that right there. Put that a little bit lower. don't make fun of my picture. And if I look at some z-axis. All right, so here we go. We're going to try to draw this. So the blue line here, x minus 1, has an x-intercept of -1, a y-intercept of 1. So that shape would look something like that. By the way, for those of you who have never drawn in 3 dimensions, it's devilish if you can pretend to not do it. And then this would have a shape that would look something like, let me make sure I've got what I wanted. Yes. 1 and then 2 would go up to 3. So y is 1, y would be 2, y would be 3. This would look something. Oh, that's what's wrong. My scale is off. So then this would go somewhere like so. This should actually be the 3 right here. 1, 2, 3. There we go. Just go with it. I'm going to get rid of the scaling because that's what's checking with me. All right. So hopefully you could see if I were to tilt this up, you would see that that would look approximately like that. So now if I took a series of squares perpendicular to the x-axis and I created heights, that's the same color, that's not really useful per se. I'll do a purple right here. You can see the shape yellow, sure, that we're going for. By the way, this is the one time I'm ever going to try to draw one of these. After that, you're all on your own. You can kind of see how that comes up. And if we go further over here, it would get smaller relatively quick. And you can kind of see how we would have shapes. So the big thing is in this question is how on earth do we determine how long the side is? And we can see from the drawing that the side is really just this piece. It would be the distance from the upper line minus the lower line. And that's what we had come up with earlier, is that if we knew that the area of the square is s squared, and the side length is determined by the upper line minus the lower line, if we simply take the integral from -1 to 2, we would take the g of x function, my linear function, minus my f of x function, and this would give me my s value, and square it. We would have this right here. Now, here's good news. If this made any semblance of sense, my attempt to draw a three-dimensional figure, which is not something I attempt very often, but if my drawing of that three-dimensional figure was good enough for you to be able to go, okay, I think I see what he was talking about that distance and why he did g of x minus f of x, and the reason why he squared it is that he wanted to find the area, and if we realize that it's just the integral of an area will give me a volume, then from here, the question, and I just realized that I totally did this, no, I did this in the right spot, squares cross sections, thank goodness. Then the rest of this turns out to be a fairly easy set of problems. See, because from this point on, all we ever have to ask ourselves is what function am I looking for? In this case, in a rectangle, we would want the area of a rectangle with h is equal to 1. So if we know h is 1, we'd have 1 times, what else? Well, we would look at our shape and realize that we would be perpendicular to the x-axis. So I'm going to draw things that are cross-sections perpendicular to the x-axis. And we can see that the length of each one of these is determined by the g of x function minus the f of x function. So in this case, it would be g of x minus f of x. Base, or height, times the base. So all we would have to do here is realize, well, this is now integrating from -2 on to 2 of that 1 times the g of x minus the f of x. Now, cool thing, it's the math class. They assume that you know that that would be a 1. This would be -1 to 2 of g of x minus f of x dx. The area of the region happens to be the volume of this particular shape with a height of 1. Which it should not be, missed the parenthesis. They would flay me for that. So there should be nothing new from that versus the first thing we solved, the area of the region, 9/2. So how could this have changed? This particular question could change in a couple ways. I'll come back to, so what are some other things that we could do? Just so we can kind of get an idea. Well, what if this were not an area of a rectangle with h equals 2, but what if this were the area of a rectangle with h is equal to 6? Well, that would mean that we would take the integral from -1 to 2 of 6 times the g of x minus the f of x dx. Or, one of my personal favorites, area of a rectangle with a height 3 times the base. Well, now that might take a little bit of thinking. So 3 times the base. So I have a height and I have a base. I know what the base is. The base of g of x minus f of x. The height is 3 times the base. Well, if the base is g of x minus f of x, then this is g of x minus f of x times 3. Or, written in integral form, -1 to 3 of 3 times the g of x minus f of x squared dx. And you can see that we can change multiple different setups. Doesn't matter what the relationship is, as long as I can identify how the relationship works, I can come up with a clean answer. Moving on, same exact thing with the equilateral triangle. Equilateral triangles, area of an equilateral triangle is going to be root 3/4 s squared. Those of you who want proof of that, you can find that somewhere online. I can provide that for you later, but that is how that would work out. Similar thing, I'm not going to go through this because this is going to follow the same procedures as a square, except you're going to have a root 3/4 that you can factor out. Then there's the semicircle. This is the one that will mess with students. So again, we want to think about the area of a semicircle. So the area of a semicircle is half a circle. So far nothing new. Integral -1 to 2, 1/2 pi perpendicular to the x-axis. Only thing I can evaluate is I can really only evaluate these cross sections. If I were to slice through any of these points, we would create cross sections with these lengths. What students will do is students will go g of x times f of x, or g of x minus f of x, and call that my length. But please recall what an r is. R is the radius. And so if r is the radius, we don't want this full length across, because remember that each one of these is going to create this semicircle. And in a semicircle, a radius is not the distance all the way across, but rather the distance to the center of each one of these. See, it's not g of x minus f of x, but rather g of x minus f of x over 2. What I will leave you with is a little bit of a generic thing, or if I were to rewrite this, I would call this pi over 8 g of x minus f of x squared dx. The last problem I want to look at is this final one. And none of the classes have done this one. So I hope that this will come out fairly easy. We're considering a region S bounded by y is equal to e to the x and y is equal to x plus 2. The region of the base is a solid. Find the volume of the solid whose cross-section are squares. Okay, I notice we know what the cross-sections are. The cross-sections are squares. So I'm like, yo, sweet. Area of a square is equal to s squared. Awesome. But then I'm going to have to read on, perpendicular to the y-axis. You see, if I start doing something like this, I'm going to mess the problem up because this is not what it told me to draw. No, didn't say draw those. Perpendicular to the y-axis, we're going to take this problem, we're going to look at it. Oh, this is so hard. Perpendicular to the y-axis. We're actually looking at these cross sections going across. What will happen is we would draw something that would look like, well, that's not supposed to be that big. We'd have something that would look like this, that would get really, 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 really tiny right about here. It would get really, really tiny way up there. So you'd have something that would look like so. Now that's going to make life a little bit more interesting because now you see by telling me that it's perpendicular to the y-axis, it's no longer a change in the y's that I'm interested in, but actually a change in where the x's are going. Which means y is equal to e to the x and y is equal to x plus 2 is not useful. I want x is equal to the natural log of y, and I want x is equal to y minus 2, because now I'm interested in how those functions are related, because now I'm perpendicular to the y. So this kind of gives you whether it's a dy or a dx problem, and then from there we can just work with it. So now I look, and the right function always seems to be the exponential, or in this case the natural log version, and the linear function will prove to be your left, because I'm dealing with a right minus left situation. So I look at this, I set up my integral. Now, because this is a dy, I want to compare what the smallest y to the largest y is. So my smallest y is apparently 0.158, and my largest y happens to be 3.146. And I'm going to look at this from the natural log of y perspective minus the y minus 2 dy. And actually, that's as hard as it gets, folks. This is not going to be terribly difficult because if you'll notice, this is going to allow you to use your calculator, much like your assignment is going to here in just a minute. So I'm working on bringing up the calculator. Smart View. There we go. All right, just bring that up. That's right, folks. Just need to wait for things to happen. Story of my life there. All right. Anybody who's a cellist has probably started having a small aneurysm right there. All right. I've talked a little while. That's starting to get a little awkward. There we go. Hey, I got a calculator. Not that it's where I want it to be. You guys can see the top of the calculator. All right. Cool. So, this turns out to be not a terrible little situation. Now, you didn't have the ordered pairs. Let's say we didn't have the ordered pairs and we were just dealing with this as the problem in your paper had told you. What I would have done is I would have realized, okay, well, I can only put e to the x, so e to the x actually, I don't want to do e to the x. I had to turn it into the natural log. So this is going to look slightly different. I'm going to call this the natural log of x as one of the functions. And I still want it to be the natural log because I want to know when these are going to intersect. And these are equivalent statements, but I'm basically turning the x's into y's in this question. And this is going to be y minus 2, as I'm going to call it x minus 2. And while the picture in the graph is not going to look exactly right, it will give us what we are looking for. So what I would do is I would go ahead and I would find where on earth these two things would intersect. Let's go over there by the 0. Intersect. First curve. Oh, we're already way over there in the negatives. I want to make sure I'm on a portion of the function that's actually defined. That looks good. That looks good. Yes. Okay, so one of my intersections is that 0.1585 that they were talking about. So I'm going to quit. I'm going to store. X is going to get stored as A. So now the A is going to be saved as that. Go back over here to my graph. I want to trace. I want to find the intersection at, oh, it's not going to do what I want it to do. Forget that it doesn't do that with intersect. Beautiful. Enter, enter, enter. Find out where that is. Intersections at that 3.14 that we were talking about for the y earlier. So X is now going to store into B. And if we remember that we put the e to the x, the natural log first and the x minus 2 second, then what we can actually do here, I can bring up the number 4 in deriv, and I can go from A to B of y1 minus y2 dx, and get a final answer of 1.949. So they could give you the problem sans these intersecting points. You can do it. The hard part with the calculator is that you have to realize that even though that says y, don't fall into the trap that I almost did. Use an x still, because that's all your calculator is allowed to use. I'm hoping that that's useful to you. That will hopefully help you as you go through the rest of the problems there, where you are looking at using the calculator to do squares, equilateral triangles, semicircles, and an isosceles triangle with a hypotenuse as the base of the solid. Ooh, that sounds like it could be a lot of fun, said nobody ever. But that's okay. So I hope that that will find you in good spirits as you finish that off, and I look forward to answering any questions that you have on Monday. Thank you, and have a great day.